Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 53. My name is Joseph Darnell, and I'm joined by the doctor in the house, Dr. Robert Carter. Hello, Rob.
Hey, Joe. What's up, man?
You know, it has been just an interesting spring, and I'm really excited to go back to the office soon. We've had thunderstorms. These are testing weeks, so we're trying to help them with extracurriculars on top of birthday parties, on top of tests. I'm tired. I need to change my shirt. I'm just exhausted right now. How are you doing?
I'm doing okay. Yesterday was a bear because I had my second COVID shot and it hit me like a freight train. But okay, we'll talk about that later if you want to.
Oh, yes. Oh.
Besides that, I'm doing just fine. Those storms yesterday were crazy.
Yeah.
I mean, I lost power at home twice. My internet went out 4 different times throughout the day. And some of those thunder shots, oh my. I mean, it rumbled for like 30 seconds.
Yeah.
It's like, what is going on?
My wife is from Oregon. She's used to storms, but not having all that much in the way of lightning. So she was just driving down the road yesterday and it blew her away when a lightning bolt flashed right down in front of her. You know, while she was driving down the road, she saw it miles away, but it was a big deal to see the lightning array.
A huge amount.
And yesterday was her birthday. So we went to the donut shop and got her donuts, and it was raining like cats and dogs.
I'm so glad I did not have to drive yesterday.
Yeah.
Because it was horrendous. Yeah.
Yeah. Now, you had a couple of other things we wanted to get to in the outline here. I see that you mentioned something that I'm unfamiliar with, transparent wood. And this is a new innovative invention. This is interesting.
Well, it's been around for a couple of years and they keep on getting it better and better. And basically, somebody realized that the reason you can't see through wood is not because of the cellulose or the chlorophyll, or no, maybe because of chlorophyll, but there's no chlorophyll in wood. It's because of the lignin, the brown stuff, the hard stuff in wood, lignin. And they said, well, we can dissolve away lignin. What happens when you do that? You're left with transparent wood.
So is it still hard, but it's transparent?
No, it's a bit floppy, but you can fill it with different things. And what this new story that we're going to have linked for everybody is that they used a derivative of citrus from actually the stuff they throw away. You can take it and make a simple chemical reaction, and if you impregnate the wood with that, it makes it hard and more clear than any other version of transparent wood they've ever done. Whoa. You can almost read through it. And it's thin. It's only, a couple of millimeters thick, but you can almost read text through it.
Interesting.
Bizarre. But now the thing is, you make a big block of this stuff can store a lot of heat.
Really?
Yeah, so you have a transparent thing that can store heat, unlike, a block of iron can store heat, but it's not transparent. And so they're thinking of all these industrial applications for transparent wood. I mean, this reminds me of Star Trek and that stupid transparent aluminum idea. But
that was a thing, huh?
You didn't see that?
No,
I guess this is a Star Trek from when I was in high school. So this is, okay, true story. I lived in the Hamptons growing up. The Hamptons, all those fancy people from New York City would go out there, all those millionaires. Yeah. Steven Spielberg had a membership at a video store that a guy at my church ran.
Nice.
So, Steven Spielberg would come down to here and rent rent VCR tapes from this guy. Nice. That's where I lived. And, my mom had a little typing service, and she had one of the world's first portable computers. It was a K-Pro 4. It had like a 4-inch green and white screen and 2 floppy disk drives. Woohoo! And the thing was transportable with a wheelbarrow, but no, you could latch it on and carry it. It was just like 30 pounds. And she started a typing service, and no one else had computers yet. It was in the early 80s, and so people would come to our house. Howard Cosell came to our house. Howard Cosell from the ABC's Wild World of Sports, that guy. And he wrote a letter to Lee Iacocca, the chairman of Chrysler.
Wow.
In my mom's office. I mean, this is great. Anyway, these guys came to my mom and they said, okay, we got a screenplay for you to type up. It was the screenplay for Star Trek 4.
Dude, I had no idea.
I read the screenplay.
Wow.
And so the thing comes out in the theaters, and I tell all my friends, this is going to be great, man. This is going to be awesome. And we go down the movie to watch it. And I didn't tell anyone what the plot was, but I knew in my head that
it was the whales.
They were going back in time to save Kirk's son who died on the Genesis planet. And so they do. They get the Klingon bird of prey and they go really fast and they go back in time to save the whales. What a giant disappointment. It's like, you ruined the movie. So, true story.
Wow.
How did we get off on that tangent?
I'm not sure.
What was that? You said something about whales. You said something about whales.
Something in the weather yesterday with a thunderstorm. And then it led one thing to another to another.
That's right. And I just told you this long, long anecdote of my early life.
And that is why Dr. Robert Carter became a marine biologist.
Because of whales. Hey, maybe. Actually, something really cool happened in space. And I was worried that it was going to interfere with this recording. I was like, come on, guys, you got to do it now. Because if you wait, and what it was SpaceX finally stuck a landing.
Nice.
SN-15 didn't blow up. Now, I've watched the other 3 launches of these things that they're building to try to get to Mars. The first one crashed upon impact. The second one landed and blew up a minute later because of fire. The third one kind of fell from the sky and blew up. But this one, they actually landed it. It went up, it paused and hovered, it came down, but the problem was it was cloudy. And so as soon as it went up, it disappeared. Wow. And so I flipped the feed from the Everyday Astronaut, which I love watching, over to the SpaceX feed, and they had the inside and outside cameras. And I was watching both at the same time, and it came back down, fell through the cloud, stood upright, and landed, and it was on fire when it landed.
Whoa!
Oh no! Oh no! Oh no! But then the fire went out, and it didn't blow up.
Oh,
so what the world just witnessed, this is unbelievable. I mean, could you think of taking a Saturn V rocket and sending it up and landing it again, only like 100 feet from where it took off?
That'd be awesome. Yeah.
It might be 200 feet. I don't know what the distance is, but it's the landing pad is right next to the launch pad. And it lands on the cement pad that they built. Every time it lands on the pad. I mean, what kind of computer control does that require? The technology is shocking. And this is all building up toward, well, first landing on the moon safely without blowing up with people on board.
Right.
And landing on Mars. And since SpaceX has got the contract from NASA to land people on the moon, because everybody else, they're so far behind, it's ridiculous. They're going to be able to develop the lunar lander at the same time as the Mars lander. In fact, essentially, NASA is now financing Elon Musk's Mars lander. If you think about it that way, because the same technology is going to be used in both places. They've got now a demonstration. They don't just bring it up and bring it down the same place. They bring it up and bring it down without blowing up in the same place. So that got me really excited. 10, 15 minutes before we started was when it finally landed.
That is super, man. In my lifetime, NASA was just winding down. Their missions were less exciting. What they wanted to do was mostly already up in space. And then we were just supporting satellite television and cell networking and GPS navigation, like nothing especially exciting. So this is really cool. Really excited to experience, get a taste of the kind of stuff that you appreciated growing up when, space exploration things were happening that were really cool.
But the SpaceX landing of SN-15 was anticlimactic because it didn't blow up. I was actually a little disappointed.
You know what you do is you land the rocket and then you shoot the fireworks. That's what you do.
But nuclear engineers and rocket scientists want the same thing. Boring days in the office.
Yes.
None of those people want exciting days because that means something really bad happened.
Yeah.
You don't want to poison half the civilized world and you don't want to blow up a rocket.
That is so cool. We're going to have to talk a lot more about SpaceX, maybe a whole episode about that from start to finish.
We talked about that a while ago, and that's on our list. An episode on SpaceX. But
I want to go back to NASA. I'd like you to talk about NASA from start to finish.
Yeah.
We haven't. It's right there. It's on the silver platter.
Oh, dude. Of course.
Yeah.
And we get to talk about, Michael Collins just died. He was 90 years old. Michael Collins, the third guy, the guy who didn't land on the moon, the loneliest man in the universe, because he was in the command module orbiting the moon. And every once in a while, he went out of radio contact with Earth. The guys on the moon, they could talk to Earth the whole time, but not Collins. He Nothing. Oh, come on, please bring me back around. Oh, hey, Houston, I'm still here. I'm still here. Anyway, that guy just died. Amazing.
Wow. Well, we're going to definitely get this into the queue.
All right, it's there. You got some news for our listeners, I hear.
Yes.
I know we've been talking about this for a while, and you took the bull by the horns and got it set up. What is this big announcement that we're about to announce?
Ladies and gentlemen, Rob and I are happy to announce that we are beginning Equinox membership.
Woohoo!
So we are calling it Equinox Plus. We wanted to think it through, make sure it was worth our while, and that we were going to give something to our listeners that they could really appreciate and sink their teeth into, their listening ears into. So Equinox Plus is going to be using Patreon. For either $1 a month or $5 a month, you can become a member and get the benefits that we would have for our members. Now, there's been a lot of buzz in and around social media and the news about Apple introducing membership programs to Apple Podcasts.
Yeah, and YouTube just started memberships also.
And then Spotify is doing it as well.
Oh, Spotify is too. Mm-hmm. Wow. Everyone's trying to get on the game.
And there's different mechanics for how YouTube and Spotify and Apple would all provide membership to listeners. And I think the overall best that we could deliver would be what Patreon has been doing already, that's tried and true and flexible.
Yeah.
Good for us on our end for engineering the back end and also providing what we want to give our listeners. So in the future, you're still getting this audio feed, these episodes. And if you want to hear more Equinox content, great or small, maybe short bonus content or maybe longer episodes, maybe a few special episodes throughout the year, we have plans. You can become a member and get that separate feed for the additional content on Equinox Plus. So we'll give you further details next time. I'm working out the kinks just to make sure it runs smoothly before I give you the link and things like that.
Also, we would love to hear from our listeners about what they might expect from Equinox Plus, especially if you already are on Patreon with any other podcast, because a lot of podcasts, a lot of podcasters are on Patreon. What do they do? What would you like to do different? Just give us some ideas. What are you expecting out of us? But notice also, listener, Joe and I are doing this because we love to do this. We've been doing Equinox now for over a year and have never asked anyone for a cent and have never even taken a dime from anybody, just because we love science and we love talking. Put those two things together and we have Equinox.
Yeah, really, we have only a few consistent costs, with the website, the server, the feed, maintaining it. And then beyond that, we would like to offer things like merchandise in the future because we would enjoy it as much as maybe our listeners. Mm-hmm. And I'm just excited to see where we can take it because in the future, we would like to be able to do more with Equinox and more podcasting down the road. We're not sure what that would be because we don't expect it to replace our paychecks in the next year or anything like that.
No, not even close.
But we're just excited to see what opportunities might be able to happen down the road.
Yeah.
We would like to explore new things and do more with podcasting than we are today. This is one of the steps on that journey.
Good explanation.
And as a reminder, not related to the membership program, but if you were interested in hearing us talk about any topic anytime, or if you had a question about something either one of us said on a previous episode or maybe a science subject came up in the news or something odd that a friend mentioned and you wanted to fact check it with us, Rob and I do want to hear your suggested topics and questions.
Yep.
So you can send those anytime to @podcastequinox on Twitter and or email us equinoxtalkshow@gmail.com. So just let us know about anything that you would like us to discuss on a future episode, and we'll see if we can fit it in. So Rob, I'm really excited to get into this topic today. I suggested it only, the day before yesterday? And it was one of those things that smacked me right between the eyes. Like, why haven't we already explored this as an episode? Because I've heard other people enjoy talking about this. I've watched YouTube content about this. I've listened to other podcasters talk about this. And it was so obvious and it was going to be so cool. How could we go for a year and not talk about the periodic table?
I don't know, because I've also heard a lot of people talk about this. I've thought about this a lot. I've taught through this before, and it never occurred to me either until you said this. Wait a minute, that's perfect. So boom, here we go.
The periodic table. If you're not familiar with it, I know one thing to get you into the spirit is to listen to the periodic table song on YouTube or on your music player. Oh, I love that song.
Oh, yeah, sure.
The periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times,
Magnesium.
We actually have that in a playlist we listen to with the kids in the car.
Wow. I think people, it's not that they're not familiar with it. I think they're terrified by it. I think most people have very bad memories of high school chemistry and how imponderable it was and how nothing made any sense and how the teacher was just talking about things and, I'm just trying to memorize something so I can pass that test. And the periodic table just didn't make any sense. What are elements? Why are they arranged like that? What do you mean they have different sizes and different masses and they're different activity chemically and what? Yeah, so because it's so opaque, we decided that we're just going to talk through a couple of things, and we're not going to do the typical way, just like everything I've ever done in the show. Forget what you learned in school. That's irrelevant. We don't want to talk about what you learned in school. Let's think of this differently, and maybe we can come to a better understanding of what this thing actually is. Fair enough?
Yeah, I think it's really exciting to explore historically how what we thought were the elements and what we thought was the periodic table at different times has changed.
Yeah.
I want the bookends first, Rob. I want the title page, and then I want to jump to read the last page of the story before we get into all the content in between.
Okay.
Yeah, so the periodic table is basically all the elements, right?
Yes.
And second, this is like the final page. Do we know all the elements, or could we discover any more? Is that likely to happen?
Okay. Yes, we know all the elements, but there might be more.
So yes, and
we know in other words, the periodic table has been filled in up to element number 118, which was not true when I was in school. Huh. There's blank spots.
How many do they have then?
Oh, maybe 110 or 12 or something like that.
Oh, okay.
But we knew there should be more out there. And then over time, someone would discover a new element and they put a place marker on the periodic table. And so at one point, all the places are filled in, but they were arguing over names.
Right. Because
that's a big deal. You can't name it after that guy. You got to name it after me, or not that university, or not this city, or this country. No. And so it took a long time for the international community to come together and actually figure out a finalized, acceptable name for all of them. The table is currently filled in, but all of the last ones are artificial.
Artificial?
They don't exist in nature. We had to make them.
What? Oh, synthesized, so to speak.
Yeah. They're so radioactive, they don't last very long, most of them.
Oh, wow.
But because we can synthesize new elements by smashing smaller elements together, is it possible to go to the next level? That is right now an open research question.
All right. Okay. Now we got to go back to the beginning of the outline now.
Yes.
I want you to explain why elements are weird, Rob.
Okay. Yeah, it's my first point I wrote down. Elements are weird. Absolutely weird. At first, nothing made sense. I mean, literally for millennia, no one could make heads or tails of different elements. But, think back in ancient times, what did they have? They had the ability to make hot fires and melt metal. And if you could separate out metals at different temperatures, well, you could separate gold from silver. Because very often gold and silver are found in the same ores. Oh, if you start heating it up, you get this stuff coming out. Later on, you get this other stuff coming out. Oh, and when they cool, they're different colors. They have different properties.
Right.
One of them doesn't tarnish. One of them does. Gold, silver. They had lead. They had mercury, carbon, but not in a pure form. And they didn't know these things were elements. They just know that we can't refine this anymore and get anything new out of it. So at the limits of their technology, and they happen to have stumbled upon several of what we now call elements, things that are indivisible, things that you can't refine, you can't purify, you can't separate, you can't do anything with it. Silver is always silver. Gold is always gold. Gold is not a mixture of gold atoms and uranium atoms. It's gold. But they didn't know that. To the Greeks, there were 4 elements: earth, air, water, and fire. You know that the 70s group Earth, Wind, and Fire?
Yeah.
Ooh, man, those guys had a groove. Anyway, yeah, that's earth, air, water, and fire. I don't know why they didn't have water in earth, wind, and fire, but whatever. That's a Greek concept that there are 4 elements.
Right.
But
I've heard about that in the science fiction, television shows, other literature.
Yeah, there was the Greeks trying to classify things. They're totally wrong. Completely, absolutely wrong. Fire is not a thing. I remember once I was looking at a bonfire and a big poof of flame came up. And then the flame disappeared. And in the same exact shape as that flame was a black poof of soot. And that's when I realized what a flame was. It was atoms releasing energy.
Oh, yeah, of course.
And this flame was a poof of carbon that went up, and it was an incomplete combustion. So I could see the carbon soot that wasn't completely burned. As soon as it cooled to below flamey temperature, I could see the carbon. It's like, oh, flames are just atoms that are hot. Cool.
It's really
But what's an atom? See, well, about 500 BC, the Greeks, again, came up with this thing they called atoms, and there's this entire atomist school. But I'm sure that the atomists were fighting like cats and dogs with the other philosophical schools, Epicureans and whatnot. I mean, they just had these schools of philosophy, and they taught that there was a point at which you could take a gold bar and cut it in half, and take half of that gold bar and cut it in half, and take another half and cut it in half. You can cut and cut and cut and cut and cut and cut, but eventually you'll reach something that cannot be cut. They call that an atom. It was what we call a lucky guess. They didn't know squat about how indivisible something was. It was completely guesswork. And we get this idea of what an atom is from the Greeks. Now, today we know that atoms are divisible. We can smash them, we can rip them in half, we can explode them, we can compress them, we can do all sorts of weird things with atoms, but only at like non-campfire energies. You can't smash atoms in an iron foundry. But way, way back in ancient times, they could smelt copper. They could get lead out of ores. I mean, they had some of the basic elements that we now know. It wasn't until 1827 that we had hints that atoms actually existed.
Wow.
What? There was a plant biologist named Brown. I think he was Scottish. He was looking at pollen floating in water under a microscope. And he said, the water's not moving, but the pollen is. But they're not all moving in the same direction. They're moving randomly.
Oh, wow. That was how you figured it out?
So he said there's something bumping into these pollen grains at random.
Yeah.
They're not flowing in one direction. They're not circulating. There's no consistent pattern to their movement. It's just, they're just jiggling. And he said, oh, well, we knew what water was. We knew that at that time, water was H2O. We already knew that. I mean, this is early. We hadn't learned it for very long, but he knew the chemical component of water. They were starting to get a hint of how massive a water molecule was. Maybe. And he said, well, things are being jostled by molecules. Therefore, water must be composed of discrete little particles. It's not a mass of goo.
Right.
Well, then Einstein in 1905, he said we should be able to use Brownian motion, which is random movement based on nucleic fluctuations or whatever, atoms bumping into each other, Brownian motion. We should be able to use Brownian motion to measure the size of atoms. Now, 1905 was Einstein's golden year. He had several, I think it was 3, monumentally earth-shattering papers that he published that year alone. And one of them was this, what I would think would be like a non-starter, Brownian motion to measure the size of atoms. Yeah, and very quickly, some other scientists took that idea, and one of them won a Nobel Prize for work he did a couple of years after Einstein's thing, where he measured the size of atoms and calculated what we call Avogadro's number. Now, his name wasn't Avogadro, but Avogadro back in 1800 said, you know what, there's this number. And now what we say is Avogadro's number is defined as the number of atoms in 12 grams of pure carbon-12. So we know carbon has several isotopes, carbon-12, 13, and 14, but we can separate them. And if you just take regular old carbon-12 and count up the number of atoms in 12 grams, it's 6.022 times 10 to the 23rd atoms. Well, that means that in 1 gram of pure hydrogen, not deuterium or tritium, you have 6.02 times 10 to the 23 grams. That means that in oxygen was water is 18, I think. Is 860? Yeah. Water is 18. Pure water, no hydrogen or deuterium in there.
Okay.
And therefore, in 18 grams of water, there's 6.022 times 10 to the 23rd molecules. Now, it sounds like what on earth? Why would anyone know that? Who cares? Well, what it does, it allows us to treat atoms in a countable way. Not just mass of atoms, but we know how many atoms are present. It's in the same way we talk about, dozens or a gross or something like that. So, yeah, you never want to say, okay, I need 3 pounds of eggs.
Oh,
what
right.
good is that? What's 3 pounds of eggs? Who cares? How many eggs do I need?
No.
Well, in the same way, we don't always want to know kilograms of atoms. We want to know Avogadro's number or moles of atoms, because counting atoms for some purposes is easier than weighing atoms. And sometimes weighing atoms is easier than counting atoms. It depends on what you want to do. So Einstein's realization led to an explosion of physics. But think about this. Rutherford didn't do his experiment that we talked about earlier on Equinox, where he shot charged particles at a thin sheet of a gold foil and saw that the particles, the protons, went right through the gold foil, except every once in a while they hit something and bounce off. And he said, oh, there must be these things we call atoms. And they're very tiny, and they consist of positively charged little nuclei. And the electrons, therefore, are distributed throughout. It's actually the opposite. They thought that electrons were like plums in a pudding, and the positive charge was distributed throughout. But he flipped it around and said, no, there's these things called atoms. So we didn't know what the atom was until 1911. That was only 110 years ago.
Wow.
And so you want to talk about elements? You want to talk about the periodic table? Dude, how can you talk about the periodic table if you don't know what an atom is?
It's hard to believe that so much of this information is recently discovered.
How quickly our explosion of knowledge has happened. It is unbelievable what we know today compared to what we did in the 1800s.
Right.
And yet they weren't stupid. And everything we know today is based on what they were doing in the 1800s and the 1700s and the 1600s. But okay, let's talk about the periodic table now. We have these things we call atoms. Atoms are indivisible. And atoms come in very different types. Some react with some atoms and some react with other atoms, and some don't react at all. And they're different sizes, and some are gases and some are solids. Some are liquids. Some are metals, as in they conduct electricity and they tend to be shiny. And some are not metals, like carbon and oxygen. And some of them are very similar in the way they react. They'll react with the same types of things in the same numbers, like lithium and sodium, and potassium. And a couple of them are magnetic. Some of them are radioactive. And some of them will kill you dead at extremely small concentrations. And other ones, you can't exist without it.
Right. I mean, basically, it's all the contents of the universe. It's all the material. It's all there.
Most of the universe is hydrogen. A small fraction of the universe is everything else.
Wow.
And so there's abundance differences here. Some are real common and some are really not common. Some of the ones took us forever to find because we couldn't find where they were. And then once we found where they were, trying to get them any reasonable concentration was hard, because like when Marie Curie discovered, I think the first one was radon. I think the second one's polonium. I'm guessing here. I should remember this. I forget. But she had to crush literally tons of ore to get enough material to study.
Wow.
And she found 2 new elements. She named one radon. It was radioactive. And the next one she named after her home country, Poland. That's where we get polonium from. That's totally cool. I mean, totally amazingly, wonderfully, amazingly cool. And now her husband died of cancer. She later on died of cancer.
Mm.
You know, the hazards of being a scientist back before we knew radiation was bad. My uncle died of cancer.
Related to scientific research?
Yep.
Hmm.
He was, this guy looked like Adonis. He was just sculpted. He was like unbelievable. The square chin, and the crew cut, and I mean, those pictures of Superman without a shirt, the 1950s Superman. That's what this guy looked like. And when he was born in 1930, 32, 35, somewhere in there, we had this magic stuff. We call it radiation. And he had what's called pyloric stenosis. The pylorus is the pyloric sphincter is the valve at the top of your stomach that closes and prevents stuff from floating from your stomach upwards into your esophagus. As a child, he had all this reflux. I said, we had this magic cure. It's called radiation. So they irradiated it. And sure enough, it fixed his pyloric stenosis. Hey, radiation is amazing.
Oh, my word. And
in his 30s, he had 4 beautiful young girls. And his wife was a nurse. And he's complaining about stuff and complaining. And his wife said, look, honey, you got to go to the doctor. So he went to the doctor. They opened him up. They took a look. They sewed him back up. Said, sorry, man, there's nothing we can do. His entire chest cavity is filled up with tumors.
Yeah.
So yeah, this has struck my family, this whole idea of radiation and elements and things like that.
Can you tell me then that all the elements break into like the liquids, the solids, the gases, and then forgive me for being rusty. Not everything is radioactive, but there is degrees on a sliding scale of how radioactive something can get.
Yes. Most things are not radioactive, but actually a lot more elements are radioactive than we think. Like our bones are radioactive because of the potassium in our bones.
So then for that reason, then just remind me what it means to be radioactive in the truest sense across the elements.
Usually when we say something is radioactive, it means it's dangerous to handle at high concentrations.
Yeah, see, that much I understand.
It'll give us cancer or kill us dead outright and things like that. Some things like radioactive iodine are extremely dangerous because they get absorbed by our thyroid gland and we get thyroid cancer very easily. But hydrogen is radioactive. Carbon is radioactive. Potassium is radioactive. So if you have a natural source of carbon, 1 out of every maybe trillion carbon atoms is carbon-14. And potassium-40 is radioactive. These are naturally occurring things that are all around us. But the background radiation is, we don't die of radiation poisoning because our bodies are robust. We can lose a molecule. We can lose a cell. Most radioactive decay in our bodies is completely irrelevant. Totally safe. It's natural. But some of those things like plutonium, not necessarily safe to handle, especially because it's extremely toxic. But uranium ore is not dangerous. It's not hardly radioactive. You have to enrich it greatly to make it such that you can use it to burn in a nuclear power plant or shove it together at high rate of speed to make it explode in a nuclear bomb. But even then, it's not. There are places in the world where there's there's uranium in the rocks that the people walk on every day. And so in that environment, there's a high level of radiation. And yet, those people might pick up more mutations than average, but they don't have a lower life expectancy. So what's radioactive? It depends on what you mean.
Okay. Makes sense. I just wanted that to inform the rest of the elements.
All right, let's talk about how people discovered these things. So we had, from antiquity, we had gold, lead, silver, zinc, a couple other things that could be easily extracted from common materials. And after you extracted it, it would never change anymore. You couldn't separate it. You couldn't divide it. And they got lucky with some of those things. They thought they were elements. Some other things, it turns out they weren't elements. Like water's not an element. But they didn't know that. You can't split water. And they didn't know that plants split water. Or they didn't know that water was formed when things burn. So they didn't get that yet. But the first new thing discovered after centuries of no discovery was in 1669. A Russian chemist was trying to look for the philosopher's stone.
Ooh, yeah. Huh.
That thing that when you touch it to anything, it can change it to another form. So lead can turn into gold.
Right.
So for some reason, in his search for the philosopher's stone, he decides to take a massive amount of urine and boil it down.
Oh, really?
What are you thinking? Anyway, he does that.
Yeah.
And he noticed a liquid that spontaneously combusts in air. He discovered phosphorus. 1669. By 1809, there are only 47 known elements. Some of the surprising ones we didn't know yet. By 1863, there are only 56 elements. Today we have 118, but back then they only had 56. And so one of the reasons why elements made no sense is we didn't have enough of them to fill in all the gaps in the table. And no one knew how to order them. We started figuring out that some of them were heavier than others. Okay. And we started figuring out that something like water was 2 parts hydrogen and 1 part oxygen. I'm not sure if they knew that yet, but we're on the verge of discovering that. So people are ripping apart molecules and figuring out the proportions of what those molecules are made of. And then this guy named John Newlands tries to arrange them in order. Now, other people have tried before, like in triads and things like that, but he put them in sets of 8. And he just ordered them according to their known mass. So hydrogen is first, and helium, oxygen, I don't even know if they knew helium yet, but oxygen, carbon, nitrogen, phosphorus, all the things we knew, he ordered them according to their mass. And he said, wait a minute, this goes in a cycle. They're in sets of 8.
Oh, interesting. Huh.
Oh, very interesting. But it wasn't until 6 years later that a Russian chemist named Dmitry Mendeleev. It's amazing how much the Russians contributed to modern knowledge before the Russian Revolution. Communism destroyed Russian science. Before that, we owe a great debt of gratitude to a lot of Russian scientists. After that, they gave us a pittance compared to what they were doing before. But Dmitry Mendeleev, he arranged things in a orderly structure and gave us our first periodic table. But what he did was he said, wait a minute, there's a gap here, and he left a space. So the first people, they just did them in order. He realized that there must be missing ones we haven't found yet. And that right there, that was the brainchild, that exact thought that led us to the periodic table.
Nice.
Now, in the notes, I included a picture of Mendeleev's table. It doesn't look like our modern periodic table. One reason is that it's upside down and backwards. Hydrogen is on the left there, and then lithium is below it.
Right.
Well, that's almost sort of, kind of, but not really. It's all cattywampus. And so it's hard to take this and relate it to our modern version of the periodic table. However, he left spaces and question marks.
Yeah, you have to start somewhere.
Exactly. But that right there made people say, what? I'm going to go find that. And sure enough, several elements were found because Mendeleev predicted an element should be there. And based on where it was in the table, because he grouped them according to chemical reactivity, they said, oh, not only should this thing have about this mass, it should react in this way with these substances. So they're able to pull out new things out of rocks that as far as they knew, that they had already pulled everything else out of. And so we have this table. And the reason it's called periodic is because it goes in a loop. You start with hydrogen, then you go to helium. And the next one, lithium, reacts very much like hydrogen. And then you scroll over to neon, and then you loop back again. You get sodium. It's very similar to lithium. But helium and neon on the other side are also very similar. They're called noble gases. These weren't discovered until 1894. Raleigh. Have we ever talked about Raleigh before?
No.
Raleigh is really important in the world of chemistry. Raleigh scattering is the reason why the sky is blue, actually. But Ramsay and Raleigh, what they did was they compressed air down into a liquid. And then they started separating, like they compress air down to liquid, and they drain off the liquid. There's still air there. Well, what's there? They compress it more. There's more liquid. They pull that up. Oh, this is something different. So we have nitrogen, oxygen, helium. Helium was completely unknown before this, and it doesn't react with anything.
Wow.
It's inert. It's a noble gas. And so they found the noble gases. But then, in very short order, they discovered argon, a noble gas that doesn't react with anything. But then, a couple of years later, Ramsay, working with some other guy, he's taking liquid argon, and instead of just like letting it evaporate, he slowly raises the pressure. And all of a sudden, all the argon evaporates, but there's still some liquid there. And in 3 months, he discovered krypton. The next month, they discovered neon. And the next month, they discovered xenon. Boom, 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 from compressed air. I'm shocked.
So, while you're going through this, it's fascinating to me, the naming system, because like you were saying, that they were arguing over what to call some of these things. And
Yes.
over my life, I remember thinking about, why were things called the things they are? Like, why is a lion a lion?
Yes.
Why do we call dogs dogs?
Yes.
And it's just fascinating to me when you get a name like Krypton, and my mind immediately goes to the Superman story and how he came from the planet Krypton, but it has nothing to do with this.
Yes. And notice most of these things have Greek or Latin roots, or they talk about what it, like radium, right? Because it's radioactive. But polonium, Marie Curie named it after, or maybe Paul Curie. No, Marie, she was Polish, named it after her home country. Europium was discovered in the late 1900s. Dysprosium, I have no idea what dysprosium is. Germanium obviously comes from Germany. Neodymium, I don't know what that means. Praseodymium, I don't know. But this is, late 1800s, these things are being discovered. So very quickly, we're filling in the periodic table.
Wow.
But then things get strange again. And you know how the table that you've seen in science class has that part that is not included in the table?
Yes, the division.
I hate that. That drives me bonkers. Why don't they stick that in? Well, because it would make it long and skinny, and it's hard to put that up onto one chart on the wall.
Oh,
but I had to search online because I wanted to find it, and I put it in the show notes just for you. The real periodic table.
Interesting.
It's on the top of the next page. That's what it's supposed to look like, and that makes so much more sense. It's helium, hydrogen, helium in the first row. Then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon in the second row. Then there's the third row. In the fourth row, there's a couple of extra ones in there. Iron, cobalt, nickel, and zinc. And then a fifth row. And then the sixth row, they added another spacer in there.
Right.
And then the seventh row, that's how it works. Well, the lanthanides and the actinides, that thing that they pull out and put on the side or underneath, we didn't figure that out until 1945. There's all these other elements. And people said, what? There are more elements? And all these elements, we may have known about a couple of them, but we didn't know where to put them. And one of the reasons why first atomic theory wasn't well enough developed, the idea that electronic orbitals aren't circular was still being resisted. And the lanthanides and the actinides are strange. I call them the rare earth elements, but they're not rare and not only found in the earth necessarily. But because the electronic orbitals that are being filled up in that region have such weird shapes, they all overlap with one another, and chemically they're incredibly difficult to separate. So we could not discover them until chemistry had advanced enough that now we can separate them. Now, this requires usually a lot of energy and usually a lot of toxic byproducts. So the rare earth industry is really frowned upon by the environmental movement. You know the picture of that kid, and he's in the mud pit in Africa, and he's ragging on Greta Thunberg, saying he's trying to get her whatever samarium or neodymium
Right.
out as fast as he can.
Yeah.
Well, one of the reasons why this stuff is coming from underdeveloped countries is because of the environmental issues of processing them here in the industrialized West. Now, China actually processes about 95% of the world's rare earth elements, which again aren't rare at all, but they process about 95% of it. And yet America, the United States, Canada, and Australia have, like 75% of the world's supply.
Dude.
Yeah, we should be independent economically with these things, but we're letting other people do it because here, with all of our labor and environmental laws, it's very expensive to process these things. I am hoping this will change, that we'll figure out ways to do this economically, quickly, cheaply, and cleanly.
Right.
But so far, it's tricky, and it's extremely specialized chemical knowledge to be able to process these things. So, young person, if you want to get into the world of chemistry, go into rare earth chemistry. Tons of money to be made there.
Interesting.
Anyway, so we have this weird table, and it's hierarchical and it's nested, and it doesn't seem to make any sense at all. And yet we can arrange it like this, and the arrangement seems to be working fine. And it took another great leap of faith. I don't know if that's the right word. Basically, we had this model of an atom, and Niels Bohr calculated the size of the hydrogen atom. And he was right. That's the size of the hydrogen atom. Now, his calculations didn't work for anything else, but for hydrogen, it worked. And then Schrödinger came along and he said, well, I'm going to apply these statistical formulae that no one else in the world, like named Carter, is ever going to understand. I don't understand the math. I don't do this math. But his formulas predicted very strange shapes for the electron clouds surrounding atoms. We know electrons really have no mass, and we know they don't orbit like the Earth orbits the sun. That's simply not true. And yet there are people telling us that, well, you can measure the position of an electron or the velocity of an electron, but not both at the same time. What? Et cetera, et cetera. We're talking about subatomic stuff here. It gets really strange. But Schrödinger's equations explain the entire periodic table, including the rare earths and why they're so weird, including why the radioactive elements are radioactive, etc. And so it has great explanatory power, but we are taking something with faith.
Sure.
And it only works for hydrogen physically, but theoretically, oh yeah, if we know that for hydrogen, we can also explain everything else. Yeah, we hope we're right. One of my favorite things about science is when we're only guessing that we're right. Anyway.
There's a lot on the table to go through.
There's so much more I want to say, but I don't know if I want to say anymore. I mean, did I really explain the periodic table and what it is and why it is?
Yeah, you've done a good job. But if you have more to say, you could make this a two-parter. Because I want you to talk about some of your favorites or some of the most infamous.
Well, my favorite is probably thorium. For no reason this named after the god of thunder.
That's really good reason.
But it was discovered by a vicar. I guess he was probably a Norwegian Lutheran. I'm not sure. On an island off of Norway. And his father was a geologist. And his vicar collected some blackish crystals and sent them to his dad. And they discovered thorium and named it after Thor, the patron god of Norway. Anyways, that's really cool. But each one of them has a fascinating story. Each one of them is amazing. Each one is different. Each one deserves a spot on the periodic table. And it's sad if most people have never heard of europium and gadolinium and terbium and things like that. But those things are actually really important for modern society. I love the memes or the lists of or the pictures, like the periodic table, but instead of the atoms, they have pictures of things that element is used in. And it's really surprising how much of our society is based on things that people can't even pronounce.
Wow.
And yet they're there.
Fascinating. Is that where you want to wrap up the periodic table?
It's too late in discussion. I don't want to get into filling up orbitals, SPD and F orbitals.
Okay.
I think that would just be overkill, and maybe some other time.
Cool.
Yeah, we can come back another day and we'll talk about electron clouds. That'd be a good topic, just electron clouds.
Okay. If you didn't know about the periodic table, you've learned a lot about it from us. Thanks, Rob. I mean, really, Rob. I mean, what kind of credit can I take for any of that?
Dude, man, first of all, you came up with the idea. Second of all, you guided the conversation, man. You're a great conversationalist.
One thing that kind of blows me away is just that point about the layout of all the elements, because you were saying they just don't want to spread it out the way it ought to be laid out. And, they break it up and they, for space and a poster on the classroom wall. That's huge. I don't remember ever coming across that information before. I love that.
And I think it actually hinders learning.
Yeah.
And prevents people from understanding chemistry.
I get that completely.
And if you actually did it for real and it's like, oh, there's a structure. Now let's learn what the structure means. And it's so much easier to grasp.
So thanks so much for joining us on this quest. And if you found this episode interesting in any way, consider sharing it with your family and friends. If you want to dig deeper into these topics, you can find links to anything that Rob wants to share in the show notes. And those are available on the website. That is nightowl.fm/equinox/53 for this episode. The show notes are also with this episode if you are subscribed to the show in an app on your phone. So just scroll up so you can see the notes. And you should also check into Biblical Genetics, which is Rob's other content. Biblical Genetics is available on Facebook and YouTube, and you can watch the videos and join the discussions in the comments. If you want to find me, I'm at JCS Darnell on Twitter, or take a listen to my other podcast, Hi-Fi, which is available at the same website. So that's nightowl.fm/hi-fi. Until next time, goodbye, Rob.
Goodbye, Joe.
And you've been listening to Equinox. I muted myself about a dozen times.
Really?
Because I was
Why?
coughing.
Oh, I didn't know that. I couldn't tell.
Yes. So
That's
I'm
funny.
so grateful because I had been using this other microphone where I couldn't easily mute. And then right around the time that the allergies began to set in, I got another microphone and I used this this little app called Mutify on my Mac. And I can press a keyboard command and it mutes the microphone. It doesn't go to the recording. It doesn't go to the stream. I'm so grateful. It's a lifesaver.
Cool. Awesomeness. Hey, I suppose we'll just save all our B notes for next time.
Yeah, in this context.
We don't.
yeah.
If it's an accidental B podcast, it means we don't have to do Bs every single week. Even though I love talking about bees. But
exactly.
Yeah,
We'll
okay.
save them this time.
All right.